Dear students, these videos are not meant to replace the course material, but they are meant to assist you. So let us start today by talking about encryption. Remember, we first want to define what it means that a scheme is an encryption scheme. For that, we need to define, first of all, spaces. A key space, let's say K, a message space M, and a ciphertext space C. Now, where are we going to use these? First of all, we want a key generation algorithm, let's call it gen, that takes as input a security parameter n in the unary format. Why? Because we want this gen algorithm to run in polynomial time with respect to n. And this gen algorithm is going to generate a key, let's say little k for us. Now, what are we going to do with this key? We want to encrypt, let's say using the enc algorithm, using this key, some message m. And this encryption is going to give us a ciphertext little c. We want to decrypt this ciphertext using the dec algorithm. We are going to use the same key here. For now, assume we are using a symmetric key encryption scheme. We will get this ciphertext and it should produce us, let's call some m prime. Once we define the gen algorithm, indeed the gen algorithm implicitly defines the key space. The key space is, you can define it as the set of all the keys that are generated through the gen algorithm. Similarly, the ciphertext generated by the encryption algorithm, the set of them implicitly define the ciphertext space C. What it means is that to fully define an encryption scheme, we need to define the message space, the gen algorithm, enc algorithm, and dec algorithm. Once we define these three algorithms and the message space, we now have an encryption scheme. Now we want to talk about what it means for an encryption scheme to be correct. We define this using a probability. So we define an experiment within the probability. First, we need to generate a key. Let's generate it through our gen algorithm and give it the security parameter. Next, we encrypt using this key. And this is going to give us a ciphertext. Following that, we will decrypt using the same key again. And this is going to give us some m prime, such that overall what we want is that this m prime is indeed equal to the m that we encrypted. Now we want this probability to be, let's say, equal to 1, which means the scheme is always correct. This k key is coming from the gen algorithm, there's no problem there. This c here is coming from the encryption as the output, there's no problem there. M prime is coming as the output here. What about m? We haven't defined them. What we want to say is that this encryption scheme is correct for all m, for all messages in our message space. So we want that for all messages in our message space, if we generate a key, then encrypt that message and then decrypt it, we will get back the same message with probability 1. You may relax this assumption, let's say by saying with probability 1 minus, let's say, some negligible function in the security parameter. In general, this is a perfectly fine correctness definition, but most of the time you will not need this negligible here for correctness, because already existing encryption schemes achieve this probability 1 correctness.